I have covered how to deal with arithmetic operations in Verilog. However, I haven't showed you how to represent numbers in Verilog. I just used them, and at some point or another, I just told you that this means 1 bit 0. So let me just expand a little bit how you represent numbers in Verilog. And the way you do it is actually utilizing this template in here. So this template in here shows me what I need to do. So this template shows me that you need to provide the sign, the size, the base, and the value, and these are a few examples. But let me just explain it with a very simple example with that 1 bit 0 that we have. So for the sign, a 0 doesn't have a sign, and anything you see in here is in bracket. That means it's optional. So any of these things here are optional. So you don't have to provide a sign, and of course by default it will be assumed to be positive. But anyway, we're dealing with some number. I'm not going to assume the sign. I just want the size. The size in how many bits do I need that number to be? And if I need it to be 1 bit, I'll just basically provide that number 1. And then you're going to have to put that little apostrophe in here, okay? And then after it, you're going to tell me the base. And the base is actually which number base you're using. Basically, what's the radix? Is it binary? Is it decimal? Is it hexadecimal? Or even octa? And as it turns out, like the names imply, it's pretty straightforward. You can do binary, you can do decimal, you can do octa, you can do hex, like the names imply. So what I did, I believe I used B, which stands for binary. And then the value you provide in here is based on that value. Okay, sorry. Let me just write it right under it so that you get to see it. So that's a 1, that's an apostrophe, and the base is B, which tells me it's a binary, and the value you provide, okay, has to match the base and the size. So if I'm telling you it's a 1 bit and I'm providing it in binary, that number could be either 0 or 1, and that will be a 0. And that represents the 1 bit 0. So let me show you a different example in here, and there's a few in the table. I'll walk you through them, but I'm just going to do this here. So I'm going to say, well, I want a 4, okay, and the base would be, let's say, binary. That means you have to provide it with a binary value that is 4-bit. So maybe 1011 is something that you're interested in. Now, if you want it in a different case, for example, if you take a look at this and you tell me, I don't know what that is this like, this is a 4 and an 8 is 12 and 13. This is 13. How much is it in hex and how much is it in decimal? Maybe you don't want to do this. So for example, you can say, well, it's a 4-bit. The size is the same, but you can provide it in decimal and you can tell me that this is 13 if that number was 13 in case, okay? Okay. Okay, what about if you want it in hex or octa? You can just do this. For example, I can give you a hex and I can give you that this should be an F for 15 or something in decimal, okay? And you can do this exactly that. So this table shows me a few things in here. So for example, let's read that one here. This tells me that you have a 5-bit and I'm providing it in binary, and this is the pattern, and that's the stored value that you see. Now, as it turns out, that Verilog, because sometimes you have many numbers, allows you to insert in the value underscores, and these underscores will be completely ignored. So for example, let's assume that you have something like this. Let's say 8, okay, and then you have binary, and instead of having 1, 1, 1, 0, and separated by space, Verilog allows you to put it 0 in here, and then 0, 1, 1, 0, underscore, sorry. So this here will be ignored, but now the number is much easier to read. Okay, you can convert this to hex and you can convert this to hex, as you probably know. All right, so the other examples in here, you can go through them on your own. What I'm going to do is I'm going to just expand or talk about the ones with the comments. So this one here tells me you have a 5-bit 0, but I only provided the 0. And as it turns out, it will just extend it to be 5 bits. It will know. The same goes in here. If you provided with 5-bit and you gave it a binary 1, it will know that 1 and expand it with 0. Z is just the sign for high impedance. We're going to see it when we talk about tri-state buffers. You probably will see it also if you have a bug in your code, okay, that something is not connected. X is a don't care or don't know, okay, the same thing in here. It's a 5-bit, and I'm going to specify it to be X's. And if you think about it in here, what it will do, it's a 5-bit, okay, but I only provided with a 3. It will do 0, 1, and it will expand these 3 in here. That's what it do. It extended the X's. And of course, I didn't talk about the sign, but the sign, this one here, all you have to do is just tell me, well, I need a -1, and it will directly convert it to its 2's complement. So this is what I'm interested in, is a 5-bit -1, and that's the stored value in here. It's the 2's complement of this little guy. Okay, so interesting things in here. So I have used numbers before in Verilog without specifying any of this. For example, I told you I want a 1 or I want a 2, and as it turns out, Verilog implements it as a 32-bit number. So if you have a 2, it will implement it as a 32-bit number 2. Okay, even though like we'll just put a 2 like somewhere in here, it'll just expand it by itself. The same goes with the -1 in here. Okay, you don't have to, again, anything you see here is in square brackets because it's optional. You don't have to specify it. For example, if you're not specifying the number of bits, it will assume it's a 32. Okay, and it'll just extend it. For example, this number in here, I didn't give it how many bits it is. I just told it that this pattern is in hex. So it figured out what it is in hex and it expanded it to 32 bits.